Good morning, everyone. Thanks for having me, and thanks for the introduction, John. So as John mentioned, my topic is this EFO decision support tool, also known as Ensemble Forecast Operations, but typically referred to as EFO. Mostly I'm going to focus on application on Lake Mendocino, since that's where it's been mostly developed. And hopefully that will serve as examples for what could be done on the Yuba-Feather, which we are also looking at EFO for Oroville and New Golden Park. So just a quick overview of my presentation. First, I'll just start off with some background, and then we'll be looking in more depth at this EFO methodology. And then we'll look at the decision support tool that was developed to help support real-time operations. And then we'll look at results for water years 2019 and 2020, where we actually implemented FIRO through major deviation requests to the core at Lake Mendocino. So EFO has been evaluated at 2 locations currently. So the first site is Lake Mendocino. That's where it was originally developed. So Lake Mendocino is located in Northern California. It's in the Russian River watershed. It's owned and operated for flood control by the Corps. And then Sonoma Water, which is my employer, operates it for water supply. This was the first FIRO pilot project, so most studies have been completed there. Currently, we've completed both preliminary and full viability assessments, and as well, we have implemented 3 major deviations. And then we've also looked at this methodology at Prado Dam, which is in Southern California in Riverside County. So this is located on the Santa Ana River. It's a larger reservoir, 173,000 acre feet, also owned and operated by the Corps. And here we're not as far along. We've completed preliminary viability assessments. So at the heart of this EFO methodology are ensemble forecasts. And currently, we use the hydrologic ensemble forecast system forecasts that are issued by the CNRC. So this is an ensemble forecast. It's issued daily up to multiple times a day. Depending on the location, we have varying number of ensemble members, but currently in the Russian River operation, we have 39 ensemble members. So it's designed to account for forecast variability or potential error in the forecast. And something that was really important in the development of EFO were hindcasts. And what these are is what the forecast would have been each day for a historical period given current forecast skill. So we've had hindcasts so far for Lake Mendocino, Prado Dam, and the Yuba-Feather system. So what this allows us to do, it allows us to test FIRO alternatives under a variety of hydrologic conditions, from droughts to floods. So really important. So I'm just going to briefly go over results of studies that were completed at these 2 sites so far. So first we have Lake Mendocino. As I mentioned, we've completed both PVA and FVA. In summary, so the most recent study completed for Lake Mendocino was the FVA. It shows a slight reduction in flood risk with this EFO methodology. As well, we have approximately 19% increase in end of flood management season storage. So that's storage leading into the dry season. So a big water supply benefit. And that was certainly a big component of that project for Lake Mendocino. So I will now move on to Prado Dam. So Prado Dam, we also see very consistent results. Here we see no increase in flood risk, possibly a slight reduction in flood risk, although further study there really needs to be done. We also see an increase in water supply, about a 6.5 increase, not as significant as Lake Mendocino, but still quite significant given this region and the value of water in this region. And here again, EFO was critical in demonstrating FIRO viability for the system as it was for Lake Mendocino. So now I'm going to move on to really the focus of my talk in explaining this EFO methodology, and then this methodology being used as a decision support tool. So just in overview, each day as a forecast is issued by the CNRC, it is routed through our operations model to generate a storage forecast. That storage forecast is then used to inform a risk analysis. And that risk analysis then informs a flood control release. And basically, this process is repeated each time a new forecast is issued, which is typically daily. So when a forecast is issued, we look out 15 days in order to generate the release for today, and then we repeat that process with the next forecast cycle. So to further explain this methodology, I'm going to walk you guys through this hindcast example. The reason I'm using a hindcast example here is because it was a big flood event. So we see some big activity in these figures, and it's just, I feel better to explain that, although we do have some real-time examples as well. So here we're looking at the Ensemble forecast using the hindcast from February 8, 1986. So this is forecasting one of the largest inflow events for Lake Mendocino, and is actually the flood of record for the lower Russian River down at Huronville. So as you can see, there's quite a bit of dispersion or spread in that storage forecast. So the challenge here is, how is this actual information? How can we take this forecast in order to generate a proposed release? Well, we do that by evaluating that forecast against the storage threshold. And for Lake Mendocino, that storage threshold is simply the top of the conservation pool, which is 111,000 acre feet, and it sits just below the emergency spillway. So what we do is we then forecast risk of exceeding that storage threshold, which is summarized here in this bottom figure. That red line is that forecasted risk. And risk here is simply the simplest form of risk. It's the probability of exceeding our storage threshold in the top figure. So what we do is we evaluate that forecasted risk against our risk tolerance curve. And this becomes our new guide curve for setting release decisions. Instead of a storage guide curve, we have this risk-based guide curve. So what the model does is it formulates the needed release in order to mitigate that forecasted risk to our risk tolerance curve. And that's shown here in that bottom figure. This is after a release decision has been made and applied. You can see our forecasted risk has been mitigated. And to do that, it estimated a release of about 2,000 CFS. And then also looking at the top figure, you can see a number of those in storage ensemble members have been reduced. So that is generally how the model is generating proposed releases. So now we'll look at how this methodology has been incorporated into a decision support tool. So we're actually using the FCO system that Kale went into. So we worked with HDR to develop an instance of the FCO for the Russian River. So I think Kale covered it really well. So I'm just going to briefly describe some of the key features for the Russian River. So each day, observations and forecasts are brought into CDEC. And then from CDEC, they feed our two models. So here we're using our EFO model. So the EFO model here is responsible for generating the proposed forecast-based releases. Those are then sent to a ResSym model, and the ResSym model further evaluates those forecast release schedules for additional system constraints and potentially tweaks them a bit. And then those are then provided to the operator through a web interface. And so that web interface, as Cale showed in his talk, it allows for some iterative refinement of those release schedules. So once the operator is comfortable, they then make a release decision. And then this process is repeated up to each day, or actually multiple times a day, during flood events where you might have additional forecasts being made by the CNRC. So here is an image of the web interface. Cale also showed this, but this is the web interface for the Russian River. So on the left-hand side, those are a table of the proposed release schedules. The right-hand side shows graphics for the user. And just in summary, so that first column, so that's so these are proposed releases based on current operations defined in the Water Control Manual. This next column are proposed releases using our EFO methodology. Here it's called risk-based. And then this projected column is what, if we were to just continue with the releases recommended from the previous day and project them in this current cycle, that's what this projected column has. And then here's the alternative, and this is the sandbox. So this really gets the heart of FIRO as opposed to forecast-based operations. So here's where the operator, Patrick Singh from the Corps, is the primary operator of Lake Mendocino. He can go in and adjust the potential proposed release schedules and then evaluate those to see how they perform for storage and downstream conditions to help make a release decision. And I should also mention that this interface also provides links to CW3E tools. So those include some of the atmospheric river forecasting tools, and then also some of the CNRC tools that will be covered later in the symposium. It's day 2. So moving right along. So we also provide these dashboards of forecasted conditions. So this top figure, this is that ensemble storage. You can see here the dotted lines also show some quantiles within those storage forecasts. And then that next figure below is the release. Here we are looking at forecasted risk. So here we're a little more complex than the example I showed you, because we have a dual objective approach where we're managing to multiple levels of risk. So we're looking at risk of exceeding our encroachment level that was approved in the major deviations. But then we're also looking at risk of exceeding that maximum conservation level. And those different risks also have different lead times that we're managing to. And the model is going to select the release that is most conservative, so the highest release based on those different calculations. And then we're also providing visuals of downstream flow. So here, this is the entire ensemble of conditions for points at Hopland and Guerneville. So Hopland is the most flood-prone region immediately downstream of the reservoir, and typically flows at Hopland govern much of the operations of Lake Mendocino. And then further downstream, we have Guerneville, which is also a very flood-prone region. So the whole intent here is, these releases are provided in the web interface. But then here we provide this dashboard so you can see the forecasted conditions and get a better understanding of why the release schedules are being recommended to the operator. So this is the forecast information component. So now we're going to move on to some results. So we'll be looking at water years 2019 and 2020 for Lake Mendocino. So here we have water year 2019. So the top figure there shows storage, and the bottom figure shows flows at Hopland. So the red line are observed conditions, and so this is how the reservoir was operated. And then the red, excuse me, I said the red line, the blue line is observed, and then the red line are simulated existing operations. So this is what would have happened if we had not pursued the major deviation. So just to point out a couple of things, we had some pretty significant atmospheric rivers in February of that year. And using the suite of decision support tools, Patrick and other operators of the Corps, they made pre-releases in order to draw storage down in advance of these events. And then you see the reservoir refill after these storage is drawn down. And so that's because of the actual storm event. But using the tools, they were able to skillfully operate the reservoir and keep storage well below our emergency spillway crest. And then looking downstream, when you compare simulated existing operations to observed, we also see that the flow regulation under FIRO also performed really well. We don't see any increases at flow above flood stage. And then also looking toward the end of the season, we also didn't really see a storage benefit that year. And that's simply because it was a really wet year. And so our simulated existing operations was able to catch up to the observed. But nonetheless, this was an excellent year to test out many of the FIRO tools because it was a very active year. And the event that occurred in late February was a pretty significant flood. So. Another component that we also provide is something we call virtual operations. So this is modeled and served up by CW3E through their website. So here we simulate multiple different water control plan alternatives in real time. And it allows us to model those and evaluate how these different alternatives would perform. So I'm not going to get into the details of that, but that's another thing that we actively pursue just to help inform the research component of FIRO for Lake Mendocino. And then I'm not sure how I'm doing on time, but I'm going to briefly go over 2020. Most of you might remember 2020 was, not a really wet year, but it was actually a very significant year for FIRO for Lake Mendocino. So in January, we had 2 atmospheric river events that allowed us to fill storage in Lake Mendocino up to the top of our encroachment level, approved under the major deviation. So this allowed us 11,000 additional acre feet. But then at the beginning of February, we started to see this forecast of this, weak AR event. But as you can see, that's the ensemble of forecasts. You can see none of them are showing anything above our maximum allowable storage level. So no flood release was made. And this is an important thing to point out because many people are very concerned that FIRO could potentially have a water supply impact because you might respond to an over forecast and release your water that you might have gained through FIRO. But at least this example, and then as well the historical analysis that we've done, that doesn't really play out. I mean, typically we don't see those type of over forecasts that are going to have really large impacts to water supply. So fast forward to the end of the season, we ended up with a lot more water in 2020, which was really critical for the current drought situation we're in. So having that 11,000 extra acre feet really allowed us to get through this year with water. We probably would have completely drained the reservoir if it were not for having that major deviation in place. So that's all I have.